Okay, so I'd like to start by thanking the organizers for giving me the opportunity to speak here. So I'm going to talk about the status of strong cosmic censorship in modified gravity, not just particularly for Lorentz violating theory. We'll see some other class of higher curvature theories as well. And this is going to be the outline. So I'll start by giving a precise statement of what do I mean by strong cosmic censorship and how to test it in a general context. Then we will see how the violation of strong cosmic censorship in GR, and then we will see if we can cure the violation by adding corrections over GR. So for that matter, we will consider two particular class of modified gravity theory, which are higher curvature theories and Lorentz violating theories. So let's start with the statement of strong cosmic censorship. What it says is that for generic initial data, all physically reasonable solutions of Einstein's field equation are globally hyperbolic. And when I say globally hyperbolic, I just mean there exists a Cauchy hypersurface on the spacetime on which you can define some initial data. And there are some regularity conditions, of course, on the initial data need to be imposed, but Einstein's equation should be able to evolve that initial data to some future point. And a spacetime is said to be globally hyperbolic if such a Cauchy hypersurface exists. And basically, as you can see, this is a statement regarding the deterministic nature of GR. However, this deterministic nature can break if there are Cauchy horizon, and as you can see in this picture, because by definition, Cauchy horizon is the boundary of the maximal development of an initial data. As you can see here, I've drawn two Penrose diagram of Reznor-Nosdam spacetime. If you concentrate on the point P1, the physics at point P1 is determined by giving initial data on this sigma 1 slice, which if you draw the past domain of dependence from that P1, you will end up in this slice, and you give initial data on sigma 1, and you should be able to predict what happens at P1. Now, if the point is inside the Cauchy horizon, this point P2, you need, now you can see that the past domain of dependence overlaps with the singularity. Now you cannot give initial data at the singularity because you do not know what is the space-time there. Therefore, if any point goes into the Cauchy horizon, if you throw a perturbation, let's say, into the black hole, if it goes into the Cauchy horizon, its further evolution after it crosses the Cauchy horizon is not determined by GR, and that we would consider here as a violation of cosmic censorship. So one must check whether the space-time can be extended beyond the Cauchy horizon, or for that matter, any kind of perturbation, not just metric perturbation. And since the space-time metric is regular at the Cauchy horizon, we know that horizon singularities are just coordinate singularities. You should be able to construct a geodesic which extends beyond the Cauchy horizon, and if that can, if you can do that, such a case would be considered as a violation of strong cosmic censorship. So is there a way to rescue it? So as one idea was proposed by Penrose, he realized that one way to rescue it is, of course, you have to prevent the particle or the perturbation to cross the Cauchy horizon. And as Penrose noticed that the Cauchy horizon is unstable with respect to small perturbation. We know that it's a surface of infinite blue shift. So if you send a perturbation, as it approaches the Cauchy horizon, it will get infinitely blue shifted. That's the nature of Cauchy horizon. And this grows exponentially, where kappa minus is the surface gravity of the Cauchy horizon. So there is a growth parameter here. So the solution to the idea of Penrose was that if you throw a perturbation into a black hole, it will ultimately grow infinitely at the Cauchy horizon. It will make the Cauchy horizon a singularity. That is, we call the mass inflation singularity. And when you encounter a singularity, the space-time will stop there. There is no further geodesic completeness you can construct. So there is no question of going beyond the Cauchy horizon. Now, the question is, can you bypass this idea of Penrose? That can you prevent the formation of mass inflation singularity at the Cauchy horizon? It turns out that there is another decay parameter associated with the perturbation. As you know, if you turn on a perturbation on a space-time, it will have some initial outburst, then you will go through some ring down phase, and that will lead to a late time decay. And in asymptotically flat space-time, the late time decay is a power law decay. Therefore, there are two parameters here. There is a late time decay of the perturbation, and there is an exponential growth at the Cauchy horizon. So if this decay can prevent or cancel the exponential growth at the Cauchy horizon, you should be able to prevent the formation of mass inflation singularity at the Cauchy horizon. Asymptotically flat black hole case, what happens? The decay is power law. Late time decay is power law. So that cannot, of course, counter the exponential growth. However, in asymptotically de Sitter spacetime, the late time decay is an exponential decay. Therefore, for some parameter, you should expect that this decay would be able to counter the exponential growth at the Cauchy horizon. And in that case, the formation of mass inflation singularity you can prevent, and particle or perturbation can cross beyond the Cauchy horizon, and that would be a violation of strong cosmic censorship. And here this alpha is the decay factor, and here the kappa minus was the growth factor. So what we should consider, and in fact the kappa alpha here represents the imaginary part of the quasi-normal mode of the perturbation that you are talking about. So therefore it is possible at late time this exponential decay would be able to counter the exponential growth at the Cauchy horizon, and this would prevent any formation of singularity. Therefore, one should look for the relative ratio between these two objects, right? This growth and the decay. So the quantity of interest in our analysis is beta, which we define as alpha by kappa minus. And as shown by Brito Cardoso, that if this beta parameter turns out to be greater than half, then the decay dominates the growth at the Cauchy horizon, and it will ultimately stop the formation of mass inflation singularity. So the violation of strong cosmic censorship has boiled down to the behavior of beta. So we can plot the behavior of beta and see whether it increases, I mean, it goes beyond half, or it always stays less than half. So as you can see, one of the important ingredients in our analysis is the quasi-normal mode. So we'll first have to obtain a quasi-normal mode of the kind of perturbation that we are talking about. So let's start with the scalar perturbation, and just to see what is going on here, we start with a simple case of resonant Nostrum black hole and study a scalar perturbation. And we will see that this scalar perturbation can be extended beyond the Cauchy horizon or not. And that statement would be captured by the fact that whether beta is greater than half or less than. The dynamics of a scalar field on a curved spacetime is of course given by this curved spacetime Klein-Gordon equation. And since the spacetime has been assumed to be spherical symmetric, you can decompose this phi in terms of spherical harmonics, and which will ultimately lead to this master wave equation. Now you impose black hole boundary condition, that is the perturbation is perfectly ingoing at the horizon and outgoing at infinity. That will give you a discrete set of frequencies, which we call quasi-normal frequencies. And of course, you have to check that these solutions are stable, so that will be detected by the sign of the quasi-normal frequency, imaginary part of the quasi-normal frequency. So once we, and there are various numerical techniques we can use to solve this equation. This is just a boundary value problem. So here we have plotted beta for L equal to 10 mode. Here L represents the multiple number. L equal to 10 mode for resonant Nostrum de Sitter. And as you can see, in the near extremal, here Q beta I have plotted against Q by Q max, where Q max is the extremal value of charge. So the parameter ranges up to Q by Q max is equal to 1. That is where the Q parameter, that is the boundary of the Q parameter. So as you can notice here, that as in the near extremal region, there is a violation of strong cosmic censorship, that the beta value exceeds the value of half. Now the question is, can we prevent this violation by adding corrections to GR? So our idea was that can we construct a class of theories where strong cosmic censorship can be saved, or at least it is better behaved as compared to GR. So we started by looking at the Gauss-Bonnet. So you have to start with theories where exact black hole solutions are there. So Gauss-Bonnet theory is one such example, and this is the action of Gauss-Bonnet theory. And of course, in 4 dimension, you know that this part is turns out to be purely topological, so it will not contribute to the field equation. However, in higher dimension, this contributes to the field equation. And the d-dimensional asymptotically de Sitter solution is of this form. So we'll we have studied in our paper that for d equal to 5, d equal to 6, and d equal to 7. And we want to see how the value of beta depends on this choice of alpha. Alpha is the Gauss-Bonnet coupling constant. So if I increase the strength of Gauss-Bonnet coupling constant, that is the modified gravity, can I save the strong cosmic censorship? And it turns out that we cannot. And in fact, here I have plot, so this plot represents L equal to 10 mode. This is L equal to 1 mode, and the below one is L equal to 0 mode. As you can see, as I increase the Gauss-Bonnet coupling constant, the curve shifts towards the left. Therefore, the violation seems to be earlier. So you have more parameter space for the violation of strong cosmic censorship. And this was exactly opposite what we expected it to be true. So the violation of strong cosmic censorship cannot be rescued by adding at least Gauss-Bonnet kind of. Now, to see that whether it's a generic feature of higher curvature theories, any higher curvature theories, or just specific to Gauss-Bonnet theories, we consider another higher curvature theory, which is pure Lovelock kind of theories, where you do not add the Einstein term, Einstein-Hilbert-Lagrangian R, rather you add this Lovelock terms only. And interestingly, there exists exact black hole solutions even in this space, in this kind of theories. So we come and notice that there is no alpha parameter here, because there is no R plus some alpha kind of correction. It's just the Gauss-Bonnet. So how we can compare it to GR? Of course, one of the interesting results is that these solutions are stable only for D greater than equal to 7 dimension. So we have to compare the 7-dimensional Gauss-Bonnet result with the 7-dimensional Einstein result, Einstein black hole spacetime. And here the F is the GRR metric component.
You have 4 minutes.
And as you can see that for the Gauss-Bonnet case, the pure Gauss-Bonnet case, the violation seems to be even earlier. So in that sense, I say that by addition of higher curvature terms, the violation of strong cosmic censorship seems to be higher. And this result we have shown explicitly for two different class of higher curvature theories, namely the Gauss-Bonnet and pure Lovelock theory. So we have concluded that this should be a generic features of any higher curvature theories, which of course need to be tested for other class of theories. But in absence of exact black hole solutions, that claims cannot be verified. So now the question is there a theory where the strong cosmic censorship is can be rescued, or the theory is well behaved as compared to GR as far as the strong cosmic censorship is concerned? And that we have found in Einstein ether kind of theory. It's a Lorentz violating theory. So basic idea is that the local Lorentz invariance is a sacred principle in GR. You start with local Lorentz invariance. However, there is no reason that you should trust Lorentz invariance up to arbitrarily high energy, because of course, the Lorentz group is a non-compact group, so there is a boost parameter there. So you cannot trust, you cannot test the Lorentz invariance up to arbitrarily high boost. So there exists, infinitely large parameter space where there can be Lorentz violation. And this is what exactly the idea of Einstein ether theory. What you do is that instead of you take a time-like vector field and couple it to metric dynamically. So instead of now a metric, your space-time has a particular direction at each space-time point, time-like direction, and that violates the boost invariance, because the Lorentz invariance is there should not be any specific direction, but in this theory there is a specific direction at every point. And this is the Lagrangian, so I'll not get into the details how the solutions are obtained. There are other class of solutions as well in this theory. I have just taken a specific class of solutions where you know that this correction C1, C2, C3, C4, these are the Einstein ether modified gravity constant. And C13 is C1 plus C3 and C14 is C1 plus C4. And we have plotted this beta again with respect to this C13. And as we have seen that as you increase C13, the value of beta decreases. And this we have checked for even other parameter space in this particular theory. And thus we have concluded that at least in Einstein ether theory, the violation of strong cosmic censorship is weaker as compared to GR. However, we have not tested it in higher dimensions. That is what I'm currently trying to do now. So there are also higher dimensional solution extension of this solution. So one need to verify this claim that this is not a property that is specific to 4 dimension, but generally holds in high dimension. Okay, so I'll conclude with this, that we have tested the strong cosmic censorship in theories beyond GR. We consider two particular class of modified gravity, that is higher curvature gravity and Einstein ether theory. And we find that in higher curvature theories, violation is stronger, while in Lorentz violating theories, the violation seems to be weaker. Yeah, I'll conclude with that. Thank you.
Questions?
So why are these Lorentz violating theory not like they seem to be unphysical, right?
This seems to be
Unphysical, right? Because there can be like the speed of light can be violated.
yeah. In those kind of theories, there can be faster than light propagations. But I mean, the fact is that, as I have said, up to what energy scale you trust Lorentz invariance, that you do not know, right? You can only test Lorentz invariance up to a certain energy. Beyond that, you do not know. So, and in fact, as you approach the Planck scale, the spacetime is expected to be discretized. And in that region,
Why?
as you approach the Planck scale, the spacetime would be expressed not as a continuous variable, right? It will be discretized. So in those regions, you expect that Lorentz invariance will break, but it may break even much before the Planck scale.
Why? Why exactly? It should be discretized.
I mean, it is expected, right? I mean, at Planck scale, the spacetime would be discretized.
But string theory doesn't break Lorentz invariance, I think.
Yeah, so this is one particular class of theories where they have studied the behavior of what if there is a Lorentz invariance. Of course, string theory does not violate Lorentz invariance, but we have not tested it. So up to what energy beyond, let's say beyond certain energy scale, we have not tested the Lorentz invariance explicitly. So you do not know what can happen.
Yeah, I was wondering, is it have you so instead of trying to modify GR, what about trying to include quantum effects?
So there are papers who actually studied this, and it turns out that the quantum effects are very tiny as compared to these classical effects. So the classical effect will always be dominant. These quantum effects are always subdominant as far as this. So in introducing quantum effects, you cannot cancel this violation.
Close to the horizon, they might be enhanced, I think. But okay, we can discuss this.
Yeah, so people have measured the contribution to this growth and decay at the Cauchy horizon, and it turns out that it is not sufficient enough to cancel this violation coming due to.
You're talking about a classical solution here?
Yeah.
I was thinking about including quantum correction to the stress tensor, to the matter stress tensor, which will lead to correction to the geometry also.
Yeah, so in that case, probably you have to do some back reaction analysis. I'm not sure what exactly would happen in that.
Okay, thank you.
Maybe we could discuss later. We're running short on time. So thanks, Akash.
Yep.